In the vast expanse of our mysterious universe, humanity's quest to find life beyond Earth takes us to unexpected places. Today, we embark on a fascinating journey to explore one of the most extreme scenarios imaginable, the possibility of life on rogue planets. These lonely wanderers, cast adrift in the cosmic ocean, challenge everything we thought we knew about the conditions necessary for life to exist. Far from any stars, warmth, and light, these nomadic worlds drift through the darkness of interstellar space, carrying their secrets through the void. What if I told you that at this very moment, life could be thriving on a frozen planet with no sun? Traveling alone through the cosmic darkness sounds impossible. Well, nature has a remarkable way of surprising us. Time and time again, we've discovered life flourishing in the most extreme environments on Earth, from the deepest ocean trenches to volcanic vents spewing toxic gases. As we venture into the unknown, we'll uncover how life might find a way to persist even in the harshest conditions the universe has to offer. We'll explore how these mysterious worlds might harbor life forms beyond our wildest imagination, adapting and evolving in ways we never thought possible. If you're ready to challenge your assumptions about what's possible in our universe, you're in the right place. This is just the beginning of our journey into one of space's most intriguing mysteries. Before we dive deeper into this cosmic exploration, take a moment to join our growing community of space enthusiasts by subscribing to Exploring the Universe. Hit that like button if you're ready to discover how life might exist in the darkest corners of space. Let's embark on this incredible journey together. Let's begin by understanding these mysterious cosmic wanderers. Rogue planets, also known as orphan planets or free-floating planets, are celestial bodies that drift through space without orbiting any star. Imagine a planet like Jupiter, but instead of circling our sun, it travels alone through the vast darkness of interstellar space. The numbers are staggering. Astronomical observations and theoretical models suggest there could be billions of these lonely planets wandering through our Milky Way galaxy alone. In fact, some scientists estimate there might be more rogue planets than stars in our galaxy. Just let that sink in for a moment. Billions of worlds floating in darkness, each potentially harboring its own mysteries. But how do these celestial orphans come to exist? There are two primary paths. The first and most dramatic is planetary ejection. Imagine a cosmic dance gone wrong. During the early chaotic periods of solar system formation, gravitational interactions between planets can become violent. Like a cosmic game of billiards, some planets are flung out of their solar systems, condemned to wander the galaxy alone. This process is particularly common in systems with multiple massive planets, where gravitational forces can create complex and unstable dynamics. The second path is perhaps even more intriguing. Some rogue planets may form in isolation, born directly from smaller clouds of gas and dust that weren't massive enough to trigger the nuclear fusion necessary to create a star. These failed star systems result in solitary planets, never having known the warmth of a parent star. These nomadic worlds challenge our traditional understanding of planetary formation and evolution. While we often think of planets as necessarily orbiting stars, these rogues demonstrate that the universe is far more diverse and complex than we initially imagined. Want to continue exploring more fascinating aspects of these mysterious worlds? Make sure you're subscribed to Exploring the Universe and give this video a like if you're finding these cosmic insights as fascinating as we do. There's much more to uncover about these solitary travelers, so stay with us as we delve deeper into their secrets. Now, let's explore the incredible challenges that life would face on these wandering worlds. The obstacles are so extreme that they seem at first glance to make life impossible. But as we'll see, nature often finds a way to adapt to even the harshest conditions. The most obvious challenge is the complete absence of solar energy. Without a host star, these planets are plunged into perpetual darkness. This creates two major problems. First, there's no possibility for conventional photosynthesis, the process that powers most life on Earth. Without this fundamental energy-gathering mechanism, any potential life forms would need to find alternative ways to generate energy. The second problem is temperature. These rogue planets are unimaginably cold. We're not talking about the kind of cold you experience in Antarctica. We're dealing with temperatures that could plummet below -200 degrees Celsius. At these temperatures, most molecular processes that we associate with life would essentially grind to a halt. Even gases like nitrogen and oxygen would condense into liquids or freeze solid. The absence of day-night cycles and seasons creates another set of challenges. On Earth, these cycles regulate countless biological processes, from reproduction to metabolism. They drive weather patterns, ocean currents, and countless other systems that life has evolved to depend upon. Without these rhythms, any potential life forms would need to develop completely different biological cycles and patterns. But perhaps one of the most severe challenges is cosmic radiation. On Earth, we're protected from harmful cosmic rays by our magnetic field and atmosphere. Many rogue planets, especially smaller ones, might lack these protective shields. Without them, the surface would be bombarded by intense radiation that could damage or destroy any known form of DNA or similar biological molecules. Speaking of magnetic fields, their absence in some rogue planets poses additional challenges. Beyond just protection from radiation, magnetic fields play crucial roles in retaining atmospheres and potentially influencing chemical processes that might be important for life. Without them, these planets would be even more vulnerable to the harsh conditions of interstellar space. These conditions might seem impossibly hostile to life as we know it. However, the key phrase here is, as we know it. Life on Earth has shown us time and time again that it can adapt to extreme conditions in remarkable ways. Some organisms can survive in boiling acid, others in radioactive environments, and some can even withstand the vacuum of space. While we're exploring these harsh realities, I want you to consider something extraordinary. What if life could evolve to not just survive, but thrive in these conditions? What if there are biological processes we haven't even imagined yet? These questions drive our scientific curiosity and push the boundaries of our understanding of life itself. If you're intrigued by these extreme possibilities, don't forget to hit that like button and subscribe to Exploring the Universe. In our next segment, we'll discover some fascinating potential solutions that nature might have found to overcome these seemingly impossible challenges. Trust me, you won't want to miss what's coming next. While rogue planets lack the life-giving energy of a star, nature's creativity in finding alternative energy sources is truly remarkable. Let's explore these fascinating potential power sources that could sustain life in the darkness of interstellar space. First, let's talk about geothermal energy. Deep beneath the frozen surface of these wandering worlds, their cores could still be active and hot, just like Earth's. This internal heat, generated by gravitational compression and radioactive decay, could create pockets of warmth, literal oases in an otherwise frozen world. Imagine vast underground oceans, heated from below by the planet's core, creating environments similar to Earth's deep-sea hydrothermal vents. These geological hotspots could maintain temperatures warm enough for complex chemical reactions and potentially life itself. Some rogue planets, especially those with significant mass, might maintain this internal heat for billions of years, providing a long-term stable energy source. But there's another intriguing possibility: radioactive decay as an energy source. This isn't science fiction. We've already discovered organisms on Earth that can harness radiation for energy. In the depths of a South African gold mine, scientists found bacteria that can use the energy from natural nuclear decay in rocks. These remarkable microorganisms use radioactive substances like uranium to power their metabolic processes. On rogue planets, similar life forms might evolve to harness the energy from naturally occurring radioactive elements. Perhaps the most promising energy source comes from chemical reactions. On Earth, we find organisms that perform chemosynthesis, creating energy from chemical reactions rather than sunlight. The most dramatic examples are found around hydrothermal vents in our deep oceans, where entire ecosystems thrive in complete darkness, powered by the chemistry of sulfur compounds and other minerals. These chemosynthetic communities show us that life doesn't necessarily need sunlight to prosper. In the case of rogue planets, various chemical reactions could provide energy. For instance, the interaction between liquid water and certain mineral formations could release hydrogen, a potential energy source for life. Other exothermic reactions involving methane, ammonia, or sulfur compounds could also provide the energy needed for biological processes. Think about it. While we're used to thinking of life depending on photosynthesis, these alternative energy sources might be just as viable. In fact, they might be more stable and reliable than solar energy in some contexts. They're not subject to day-night cycles or seasonal variations, providing a constant, dependable energy flow. What's particularly fascinating is that these energy sources could work in combination. A rogue planet might harbor life forms that use different energy sources in different environments. Some powered by geothermal heat in deep oceans, others utilizing radioactive decay in rocky substrates, and still others thriving on chemical energy from mineral reactions. These possibilities remind us that life's ingenuity in finding energy sources might far exceed our current understanding. Every time we think we've found the limits of where life can exist, nature surprises us with new adaptations and possibilities. If you're as amazed as we are by life's potential to harness these alternative energy sources, show your support by hitting that like button. Subscribe to Exploring the Universe to join us on more journeys into the extraordinary possibilities of life in our cosmos. Up next, we'll explore the specific environments where these energy sources might support thriving ecosystems on rogue planets. Stay tuned. The story only gets more fascinating from here. Now that we understand the potential energy sources, let's explore the environments where life might actually exist on these mysterious worlds. You might be surprised to learn that beneath their seemingly inhospitable surfaces, rogue planets could harbor several types of potentially habitable environments. Let's start with what might be the most promising habitat: subsurface oceans. We don't need to look far for evidence that such environments can exist. Right here in our own solar system, moons like Europa and Enceladus harbor vast liquid oceans beneath their icy crusts. These oceans remain liquid despite the freezing temperatures of space, maintained by internal heat and tidal forces. On rogue planets, similar oceans could exist, kept liquid by the planet's internal heat. These underwater worlds could be enormous, potentially containing more liquid water than all of Earth's oceans combined. Protected from the harsh conditions of space by kilometers of ice, these oceans could provide stable environments where life might evolve and thrive. The interaction between water and mineral-rich rocky cores could create chemistry similar to Earth's hydrothermal vents, providing both energy and the building blocks for life. Another fascinating possibility lies in dense atmospheres. Some rogue planets, particularly the larger ones, might retain thick atmospheric blankets of hydrogen and other gases. These atmospheres could create a powerful greenhouse effect, trapping whatever heat the planet generates internally. Think of Venus, where the thick atmosphere creates surface temperatures hot enough to melt lead. Now imagine a similar principle, but balanced to maintain more life-friendly temperatures. Perhaps the most intriguing environments are the geothermal caves and fissures. Imagine vast networks of underground caverns heated by the planet's internal warmth. These could create protected microenvironments where temperatures remain stable and chemical reactions provide constant energy sources. On Earth, we find complex ecosystems in similar cave systems, completely isolated from the surface world. These underground havens could provide shelter from both the extreme cold and cosmic radiation of space. These caves might even contain pockets of trapped gases, creating local atmospheres, or house underground lakes and streams maintained by geothermal heat. The walls of these caverns could be home to chemosynthetic organisms, creating the foundation for more complex ecosystems. What's particularly fascinating is how these different environments might interact with each other. Underground oceans could connect to networks of heated caves. Dense atmospheres might create pressure conditions that allow for liquid water in certain surface features. The possibilities for these interconnected habitats are truly mind-boggling. Isn't this absolutely fascinating? The idea that life might find refuge in these hidden sanctuaries, far from any star's light, really pushes the boundaries of what we consider possible. If you're finding these possibilities as incredible as I do, take a moment to show your support by hitting that like button, and make sure you're subscribed to Exploring the Universe. We've got so much more to uncover about these mysterious worlds and the potential for life in the cosmos. In our next segment, we'll delve into what forms of life might actually inhabit these environments and how they might have adapted to these extreme conditions. Trust me, what we're about to explore will challenge everything you thought you knew about the requirements for life. Stay with us. The journey through these cosmic mysteries is just getting started. Let's venture into one of the most speculative yet fascinating aspects of our journey, the potential forms of life that might exist on rogue planets. While we can only hypothesize about these creatures, our understanding of extreme life on Earth provides some intriguing clues. First, let's consider extremophiles, organisms adapted to extreme conditions. On Earth, we've discovered microorganisms thriving in environments we once thought impossible for life. In the freezing valleys of Antarctica, creatures called cryptoendoliths survive inside rocks in temperatures well below freezing. But life on rogue planets would need to go even further. Imagine organisms with ultra-slow metabolisms, perhaps taking years or even decades to complete processes that Earth organisms accomplish in hours. These beings might exist in a state of near-suspended animation, using minimal energy to maintain their basic life functions. They could have evolved extraordinary molecular adaptations to prevent their cellular structures from being destroyed by extreme cold, similar to Earth organisms that produce natural antifreeze proteins. These creatures might develop remarkable efficiency in energy usage, perhaps storing energy in completely novel ways we haven't yet discovered. Think of them as cosmic hibernators, but on an extreme scale, taking advantage of rare energy pulses and then surviving on those reserves for extraordinary periods. But perhaps even more fascinating is the possibility of life based on alternative solvents. While Earth life uses water as its primary solvent, other liquids could potentially serve this function in extremely cold environments. Liquid ammonia or methane, for instance, remain fluid at much lower temperatures than water. On Saturn's moon Titan, we see lakes of liquid methane. Could similar chemistry support life on rogue planets? Such organisms would need completely different biochemistries than Earth life. Their cellular membranes might be composed of different molecules, their genetic material might be stored in different ways, and their metabolic processes would operate under entirely different chemical principles. It's a reminder that our Earth-centric view of life might be extremely limited. One of the most captivating possibilities is the potential for bioluminescent organisms. In a world of perpetual darkness, the ability to produce light could be a crucial evolutionary advantage. We see this on Earth in deep-sea creatures, but imagine entire ecosystems built around biological light production. These bioluminescent organisms might use their light-producing abilities for various purposes. Some might use it to attract prey, like deep-sea anglerfish. Others might use it for communication, creating complex light-based languages. Imagine vast colonies of organisms creating beautiful displays of living light in the darkness, perhaps using different colors or patterns to signal different messages. Some might even use bioluminescence in symbiotic relationships, one organism providing light while another provides nutrients, creating intricate networks of interdependence in the darkness. These light displays could create entire ecosystems where organisms navigate, communicate, and survive, using only biological light as their guide. What's particularly intriguing is how these different adaptations might combine. Picture organisms that use alternative solvents in their cells, maintain ultra-slow metabolisms, and produce bioluminescence, all while surviving in temperatures that would freeze Earth life solid. The possibilities for such combinations are endless, limited only by the fundamental laws of chemistry and physics. These hypothetical life forms remind us that life's potential for adaptation might far exceed our current imagination. Every time we think we understand the limits of what's possible, nature surprises us with its creativity and resilience. If these possibilities excite your imagination as much as they do mine, take a moment to hit that like button. Don't forget to subscribe to Exploring the Universe. We're continuing to uncover the mysteries of potential life forms across the cosmos, and you won't want to miss what's coming next. In our following segment, we'll delve into how these hypothetical organisms might evolve and adapt over time in their isolated worlds. The story of life on rogue planets is far from over. Let's dive into one of the most crucial elements for life as we know it: water. On rogue planets, the story of water takes fascinating twists and turns, challenging our understanding of how this vital molecule might support life in the depths of space. On the surface of these wandering worlds, water exists in a state very different from what we're familiar with on Earth. At temperatures potentially reaching below -200 degrees Celsius, surface water ice would be harder than granite. But this isn't your ordinary ice. At these extreme temperatures, water ice forms exotic crystalline structures we rarely see on Earth, creating what scientists call exotic ice. However, the real magic might be happening beneath the surface. Despite the frozen exterior, many rogue planets could harbor liquid water deep underground. The intense pressure combined with geothermal heat could maintain vast subsurface oceans, much like those we suspect exist within Jupiter's moon Europa. These underground oceans might be more stable than Earth's oceans, protected from external disturbances and maintaining consistent conditions for billions of years. Water's role as a universal solvent makes it particularly special. Its unique molecular properties, the way it forms hydrogen bonds, its polarity, its ability to dissolve both polar and non-polar substances, make it incredibly efficient for biological processes. It's no accident that every form of life we've discovered on Earth requires water in some form. Water provides the perfect medium for transporting nutrients, facilitating chemical reactions, and maintaining the complex molecular structures necessary for life. But here's where things get really interesting. At the extremely low temperatures found on rogue planets, we need to consider alternatives to water as a biological solvent. While water might exist in liquid form underground, surface-dwelling organisms might need to utilize entirely different liquids for their biological processes. Imagine life forms using liquid methane as their primary solvent, similar to what might exist on Saturn's moon Titan, or consider organisms utilizing liquid ammonia, which remains fluid at much lower temperatures than water. These alternative solvents could support entirely different biochemistries, alien life that functions in ways we're only beginning to theorize about. Some scientists have even proposed the possibility of mixed solvent systems, where organisms might use different solvents for different biological processes. Picture a life form that uses water for some functions in warmer, deeper regions, while employing methane or ammonia-based processes near the frigid surface. The presence of these various solvents could create unique layered ecosystems. Deep underground, water-based life might thrive in familiar ways. Moving upward, we might find transition zones where multiple solvents interact, creating unique chemical environments that could support novel forms of life. Near the surface, purely methane or ammonia-based organisms might dominate. What's particularly fascinating is how these different solvent-based ecosystems might interact with each other. Could there be organisms that serve as bridges between these different chemical worlds? Might there be complex food webs that span multiple solvent systems? These questions push us to expand our understanding of what's possible in biological systems. While water remains the prime candidate for supporting life as we know it, the extreme conditions on rogue planets force us to consider a much broader range of possibilities. If you're finding these chemical possibilities as mind-bending as I do, show your support by hitting that like button. And don't forget to subscribe to Exploring the Universe. We're continuing to unravel the chemical mysteries of life across the cosmos, and there's so much more to discover. Coming up next, we'll explore how these different solvent systems might influence the evolution of life on rogue planets. Stay with us. The chemistry of life is about to get even more fascinating. As we delve into the evolution and adaptation of potential life forms on rogue planets, we encounter a landscape shaped by unique evolutionary pressures. These isolated worlds present challenges that are both extreme and fascinating, compelling life to adapt in ways we have yet to fully comprehend. One of the most significant pressures is the perpetual darkness found on rogue planets. Without a sun to provide light, life would need to develop entirely new strategies for survival. In this environment, organisms might evolve sensory adaptations that allow them to navigate and thrive in complete darkness. For instance, bioluminescence could become a crucial evolutionary trait. Imagine organisms that emit light, using it not only for communication, but also to attract prey or mates in the endless night. This adaptation could create intricate networks of life, where light becomes a primary means of interaction and survival. Moreover, the absence of sunlight means that traditional photosynthesis is off the table. In response, life on these planets might innovate in energy acquisition. Instead of relying on sunlight, organisms could evolve to harness energy from geothermal sources or chemical reactions within their environments. These adaptations would challenge our Earth-centric view of life, showcasing the remarkable creativity of biological processes in extreme conditions. Energy conservation mechanisms would also play a pivotal role in the survival of life on rogue planets. In an environment where energy is scarce, organisms might develop ultra-slow metabolisms, allowing them to extend their survival over long periods. Imagine creatures that can enter a state of suspended animation, conserving energy for years or even decades until conditions become more favorable. This ability to hibernate or slow down metabolic processes would be essential for enduring the harsh realities of their environment. As we consider the potential for radically different life forms, we must think beyond the familiar structures found on Earth. Life on rogue planets might utilize alternative molecular architectures, diverging from the carbon-based biochemistry we know. For example, organisms could potentially use silicon-based compounds or even entirely different solvents, like ammonia or methane. This shift would lead to the emergence of life forms with unique cellular structures and metabolic pathways, fundamentally altering our understanding of biology. Additionally, the life cycles of these organisms could be profoundly different from what we are accustomed to. On Earth, most life forms experience relatively rapid growth and reproduction cycles. In contrast, Life on rogue planets might evolve extremely long life cycles, adapting to the scarcity of resources and the need for energy conservation. These organisms could take years to reach maturity, with reproductive events occurring infrequently, perhaps coinciding with rare bursts of energy or environmental changes. This interplay of unique evolutionary pressures and the potential for radically different life forms offers a glimpse into the extraordinary possibilities that may exist on rogue planets. As we continue to explore these cosmic wanderers, we are reminded that the resilience of life knows no bounds, and its ability to adapt is limited only by the laws of chemistry and physics. The story of evolution on rogue planets is not just a tale of survival, it is a testament to the boundless creativity of life in the universe. Detecting life on rogue planets presents a set of formidable challenges, primarily due to their unique environmental conditions and the absence of traditional indicators of habitability. As we explore the intricacies of this endeavor, it becomes clear that innovative methods and technologies will be essential in our search for extraterrestrial life in these distant, dark worlds. One of the most significant challenges in detecting life on rogue planets is their vast distances from Earth. These planets drift through interstellar space, often millions of light years away, making them incredibly difficult to observe. The sheer distance limits the amount of light that can reach us, often rendering these planets too faint to detect with current telescopes. Moreover, the absence of a nearby star means that rogue planets do not reflect much light, further complicating our observational efforts. As a result, traditional methods of detecting exoplanets, such as transit photometry, which relies on a planet passing in front of its star, are not applicable. In addition to the challenges posed by distance, the perpetual darkness of rogue planets creates a lack of typical atmospheric biomarkers. On planets orbiting stars, scientists often look for gases such as oxygen, methane, and carbon dioxide in the atmosphere, as these can indicate biological processes. However, rogue planets lack the consistent stellar illumination that drives photosynthesis and other life-sustaining cycles. Consequently, the atmospheric composition of these planets may differ significantly from that of Earth-like planets, making the search for familiar biomarkers more complex. Despite these challenges, there are potential methods for detecting life on rogue planets that hold promise. One such method is the analysis of atmospheric composition through spectroscopy. This technique involves measuring the light spectrum that passes through or reflects off a planet's atmosphere. For gas giants, which may be more easily detected due to their size, scientists can analyze variations in light absorption to identify specific gases present in the atmosphere. While rogue planets may not have the same dramatic atmospheric signatures as their star-orbiting counterparts, unique chemical markers could still be present, hinting at biological activity or geological processes. Another promising approach is the search for thermal or chemical anomalies. Rogue planets, despite being distant and dark, may still exhibit heat generated from internal geothermal processes. By using infrared telescopes, scientists can detect these thermal signatures. If a rogue planet has subsurface oceans or geothermal activity, it could release heat detectable from Earth. Similarly, researchers could look for unusual chemical signatures in the surface or subsurface materials, which might indicate the presence of life or life-supporting processes. For example, specific combinations of chemicals resulting from biological activity could create detectable patterns that stand out against the backdrop of a planet's geological composition. In conclusion, while the challenges of detecting life on rogue planets are significant, advancements in technology and innovative methodologies provide hope for future discoveries. By leveraging spectroscopy to analyze atmospheric compositions and searching for thermal and chemical anomalies, scientists may unlock the mysteries of these enigmatic worlds. The pursuit of life on rogue planets challenges our understanding of where life can thrive, urging us to expand our definitions of habitability and inspiring a deeper exploration of the cosmos. As we delve into the scientific perspectives on the possibility of life on rogue planets, the insights of leading researchers in the field shed light on the profound implications of such discoveries. Two prominent figures, Dr. Sarah Seeger and Dr. Avi Loeb, provide significant contributions to our understanding of habitability and the potential for life in the cosmos. Dr. Sarah Seeger, an astrobiologist and professor at MIT, emphasizes the need to rethink our definitions of habitability. Her assertion that life as we don't know it may exist in conditions we consider impossible highlights a critical shift in scientific thinking. Traditionally, the search for extraterrestrial life has focused primarily on planets orbiting stars, where conditions are thought to be more favorable due to the presence of sunlight. However, rogue planets challenge this paradigm by existing in isolation from any stellar influence. Seeger's work encourages researchers to consider a broader range of environmental conditions under which life might thrive. This includes not only rogue planets, but also extreme environments on Earth, such as deep-sea hydrothermal vents and acidic lakes, where life has adapted in remarkable ways. By expanding our definition of habitability, scientists can explore the potential for life forms that utilize alternative energy sources, biochemical processes, and survival strategies. For example, life on rogue planets might harness geothermal energy or chemical reactions, demonstrating the resilience and adaptability of life in harsh conditions. Dr. Avi Loeb, an astronomer at Harvard, adds another layer of significance to the discussion. He states, the discovery of life on a rogue planet would be revolutionary, challenging our understanding of the requirements for life in the universe. This statement underscores the transformative impact that such a discovery would have on the field of astrobiology and beyond. Finding life in an environment previously deemed inhospitable would not only expand our understanding of where life can exist, but also prompt a re-evaluation of the necessary conditions for life itself. Loeb's perspective highlights the broader implications for scientific inquiry and exploration. If life can thrive on rogue planets, it suggests that our current models of planetary formation and habitability may be incomplete. This realization could lead to new avenues of research, prompting scientists to investigate a wider array of celestial bodies, including those previously overlooked. It also raises intriguing questions about the potential for life to exist in other extreme environments throughout the universe, such as in the clouds of gas giants or on icy moons. Furthermore, the implications of discovering life on rogue planets would extend to philosophical and existential considerations. It would challenge humanity's understanding of our place in the universe, suggesting that life may be far more common and diverse than we have previously imagined. Such a finding could reshape our views on the uniqueness of Earth and the potential for interstellar life. In summary, the perspectives of Dr. Sarah Seeger and Dr. Avi Loeb illuminate the transformative potential of discovering life on rogue planets. Their insights encourage a redefinition of habitability and challenge the assumptions that have guided astrobiological research. As we continue to explore the cosmos, the possibility of finding life in the most unexpected places not only expands our scientific horizons, but also deepens our understanding of life's resilience and adaptability in the universe. The discovery and study of rogue planets have revolutionized our understanding of astrobiology, forcing us to radically rethink our assumptions about where life might exist in the universe. Let's explore how these lonely worlds are transforming our search for extraterrestrial life. The traditional concept of a habitable zone, that narrow band around a star where liquid water can exist, is being completely reimagined. We now understand that habitability extends far beyond the warming rays of stars. Rogue planets demonstrate that life-supporting environments might exist in the dark spaces between stars, dramatically expanding the potential locations where life could flourish in our galaxy. Think about this. If life can exist on rogue planets, the number of potentially habitable worlds in our galaxy doesn't just increase, it explodes exponentially. We're no longer limited to looking at star systems. Every dark region of space, every seemingly empty expanse between stars could harbor worlds teeming with life. This realization is nothing short of revolutionary for our search strategies. Our criteria for detecting potential biosignatures need significant revision. Traditional methods focused on finding Earth-like planets orbiting Sun-like stars may be far too limited. We need new detection techniques and instruments capable of identifying the unique signatures of life that might exist on these starless worlds. This could include looking for specific atmospheric compositions, thermal signatures from subsurface oceans, or even signs of geological activity that could support life. Perhaps most intriguingly, rogue planets might offer something unique, extraordinary stability over immense time periods. Without a star's variable influence, these worlds could maintain consistent conditions for billions of years. Imagine the evolutionary possibilities when life has billions of years to adapt and develop in a stable, albeit extreme, environment. These planets might be perfect laboratories for long-term biological evolution, free from the disruptions that stellar systems experience. The implications for interstellar life are particularly fascinating. Rogue planets could serve as natural spacecraft carrying their biological cargo through the galaxy. As they drift between star systems, they might act as bridges for life spread across cosmic distances. This raises profound questions about panspermia, the hypothesis that life can spread through space. Could rogue planets be nature's own mechanism for dispersing life throughout the galaxy? We must also consider how this affects our search for intelligent life. If civilizations could evolve on rogue planets, they might develop in complete isolation, with radically different perspectives and technologies than star-dependent life forms. Their technology might be based on completely different principles, adapted to their unique environment. This means we might need to fundamentally rethink our SETI strategies and the signatures we're looking for. The existence of rogue planets challenges us to expand our imagination about life's potential in the universe. We're learning that life might be more resilient, more adaptable, and more widespread than we ever imagined. Every new discovery about these wandering worlds adds another piece to the puzzle of life's possibilities in the cosmos. As we continue to explore these implications, we must remain open to the possibility that life in the universe might be far more diverse and widespread than we ever imagined. The dark spaces between stars, which we once thought empty and lifeless, might harbor some of the universe's most extraordinary secrets. If these revelations about life's potential in the universe fascinate you as much as they fascinate us, make sure to hit that like button and subscribe to Exploring the Universe. We're constantly uncovering new insights about life's possibilities in the cosmos, and you won't want to miss our upcoming explorations. Stay curious and keep looking up. The universe has many more secrets to share. As we reach the end of our cosmic journey, exploring the possibility of life on rogue planets, we find ourselves standing at the frontier of human knowledge, where science and imagination intertwine. What we've discovered today challenges our fundamental assumptions about life in the universe and reminds us of a profound truth. The cosmos is far more extraordinary than we often dare to imagine. Throughout human history, we've consistently underestimated life's tenacity and adaptability. From the scorching depths of volcanic vents to the frozen wastes of Antarctica, life has surprised us time and time again. Now, as we contemplate the possibility of life on wandering worlds in the darkness between stars, we're pushing the boundaries of what we consider possible even further. The very existence of rogue planets teaches us an important lesson about humility in science. Just decades ago, we didn't even know these cosmic wanderers existed. Now we believe there might be billions of them in our galaxy alone. What other extraordinary discoveries await us in the vast cosmic ocean? While the existence of life on these lonely worlds remains speculative, the possibilities we've explored today remind us that we must keep our minds open to the unexpected. Nature has a remarkable way of finding solutions to seemingly impossible challenges. Perhaps, at this very moment, forms of life we can barely imagine are thriving in the darkness of interstellar space, adapting and evolving in ways that would revolutionize our understanding of biology itself. Think about it. Somewhere out there, drifting silently through the cosmic void, a rogue planet might harbor life in its subsurface oceans or deep within its warm caves. Life that has never known the light of a star, yet found its own path to existence. Life that tells us the universe is not only stranger than we imagine, but stranger than we can imagine. And now, I have a special invitation for you. If this journey through the cosmic unknown has ignited your sense of wonder, don't let this be the end of your exploration. This is your chance to become part of something bigger, a community of curious minds and cosmic explorers right here on Exploring the Universe. Hit that subscribe button right now to join us on future adventures into the mysteries of space. Every week, we venture into new frontiers of scientific discovery, challenging assumptions and exploring the extraordinary possibilities that lie in the cosmos. Remember to ring that notification bell so you never miss an upload. If you found today's journey fascinating, smash that like button. It really helps other curious minds find our content. Share this video with your friends who love science and discovery. Let's spread the wonder of cosmic exploration far and wide. And don't forget to join the conversation in the comments below. What do you think about the possibility of life on rogue planets? What other cosmic mysteries would you like us to explore? Your thoughts and ideas help shape future episodes of Exploring the Universe. This is more than just a YouTube channel. It's a gateway to understanding our place in the vast cosmic ocean. Together, we'll continue pushing the boundaries of knowledge and imagination, venturing into the unknown with curiosity as our guide. Until our next adventure among the stars, or perhaps beyond them, keep looking up, stay curious, and remember that in the infinite expanse of space, anything is possible. This is Exploring the Universe, where every end is just a new beginning. See you in our next cosmic journey.